Hello everyone, thank you for coming today. That's so many. They took periodic maximum 5 people, so nice to see that many of you came. My name is Matthias, and I did my master thesis work on this topical classification on images Wikipedia. I did this with Pablo and Periodic as supervisors, and then some people from Miriam, Tiziano, and Bob from EPFL, the school where I was doing my exchange studies for 1 year. And yeah, so I guess many of you know what image classification is as computer vision, computer science people, but you may wonder what a topic is. So we define a topic as a general concept that can englobe several visual objects. So I just put a lot of examples of images that I like. Here's Lausanne, where I did my exchange. Here's an image of the calling of St. Matthew by Jesus, and there's the best team ever in '94. So objects here, we see a church, we see a sky, we see some mountains, but the topics that we want to capture is architecture and landscape, for instance. In the middle we have some people, we have a window, so those are the objects, but the topic that we want to capture there is art and belief. And in the end we see people, we see some trees in the background, but the topics in that image is people and sports. So I hope you kind of understand what I mean by a topic here. Yeah, let's classify them. So let me motivate the project first. So I'm doing this project in Wikipedia. Wikipedia has around many users. Only English Wikipedia has 800 million unique users, and it has 10 billion monthly page views. That's very much. That's just huge. And then at the same time we have 38,000 monthly active editors, people that help keep quality of Wikipedia. And the proportion you can see here is 1 editor by 21,000 users. That's just very unproportional. Let me just show you what the tasks the editors do. They improve article quality, they welcome new volunteers, and they also check grammar, they add images, they check if images are good, and so on. As you can see, it's very disproportional. So something we can conclude from this is that we really need to automate all of this, otherwise it's really unreasonable that 1 people takes care of 21,000 people. But what do we want to automate? That's the question. So Wikipedia, as we all know, is made of a lot of text. We have 6.5 million articles in English Wikipedia only. And for that, we already have an automation system called ORIS. ORIS provides topical classification of articles. So if you give it an article with text, it gives you back a set of topics. It gives you a quality score of the reliability of the grammar of the article, and it also does vandalism detection. Let me just give you an example of how powerful this ORIS thing is in vandalism detection. So Wikipedia receives around 100,000 daily edits, and let's estimate that one editor can review 10 of those edits per minute. This means in total that 166 labor hours are needed per day, and if you divide it by the number of editors doing 2 hours a day, we have 83 volunteers doing 2 working hours a day. And then using ORIS, it can reduce the need of those edits, of those reviews by 90%. So 90% are easy ones, and then a human doesn't need to look at it. And then using ORIS, you can get down to, thank you Zoom, but that means 8 volunteers doing 2 hours a day. So that is a very huge difference that makes it possible to keep Wikipedia alive, especially in smaller Wikipedias that don't have 8 volunteers available. Yeah, so we looked at text. Text is okay, it's doing fine. But then when we look at images, we have a pretty similar number of images to articles, 3.9 million, but we don't have any similar systems to ORIS. So that is the problem that was presented by the Wikimedia Foundation, the Wikipedia Foundation to us at EPFL. And the problem that they identified is that images are lacking labels. There's very bad metadata relating classifying images in Wikipedia. And then you can ask me, as a computer vision people, like, why don't you use a standard image classifier that you see I don't know, pretty easily online? Why don't you classify guitar as a guitar, a microphone as a microphone, and so on? But the interesting thing here is that we want to capture not only this, we know that these two things here, they're pretty similar. We want to classify all four of them as music. So not only the semantical objects in the image, but also the other bigger context. So the problem is not that images are lacking labels, they're lacking topical labels. So they gave us this task of building a custom topical classifier. The applications of such a system, if it gets used by Wikipedia later, has both research and practical applications. Research applications are, for instance, finding visual knowledge gaps. So are biographies less represented than, I don't know, belief or art? Are, I don't know, people less represented than food or whatever? So this is very interesting for researchers. And then explain reader interaction. We want to understand if readers that interact better or in different ways with between biographies or food articles. And then more practical applications. Similarly to text, we want to implement this visual vandalism thing. That is pretty common in Wikipedia, that someone wants to be funny and then he changes the image completely, but it keeps the same image name. That is very, very hard to find, and that can be solved with such a system as ours. And then the second one is suggesting images. The bigger idea is just to improve the quality of Wikipedia content. So I said a lot of things now, let's just recap. Wikipedia is really big in its task automation. So text tasks are automated using ORs, while image tasks are missing automation. Finally, to automate image tasks, we need to classify them with topical labels. Everybody okay with that? Nice. It's okay, what's the matter? Just do it. So now I'm going to present you some challenges of doing this that we are set out to do. The first one, I just put up a lot of things here. Let me just go through them with you. So this project is made by me, and then this other guy, Francesco, at EPFL, who did this project together during the past semester and during this semester. He's developing the ground truth labels, the topics. So he's linking topics to the images. So the first problem is that the ground truth labels that I use in my classifier, they are not human ground truth. They are machine ground truth. They are Francesco's ground truth. Francesco's algorithms ground truth. So that is pretty hard. Introduces some inconsistencies, some noise that I'm going to show you later. And then here is the taxonomy, the structure, label structure that we developed together. There are in total 31 labels. There's this 4 big labels: science, technology, places, society, culture, and so on. 31 in total. So that is the first challenge. We have prediction ground truths. Later, we have a very imbalanced label distribution. And notice that this here is in log scale, so I don't know exactly the number, but yeah, there are a lot more images of society than images of belief or images of food. And that, as you might know, introduces a lot of problem in machine learning algorithms in general. So that is the second thing. Third thing, so this data set in Wikipedia has a very peculiar image distribution. Unlike data sets that you might know, such as ImageNet, Coco Visual stuff, and I don't know, those number data sets as well. It is very similar images, but Wikipedia you have everything. You have diagrams, you have people dancing, you have biographies, you have cities, history, and that's a challenge in itself. And fourth one, as you already told you, is that we want to classify them in topics and not objects. So yeah, a lot of problems. You might ask, what is this guy going to do now? What is the scope of the thesis? So we wrote 3 research questions. The first research question has to do with mitigating the consequences of imbalanced data. The second research question is how to do a hierarchical classification and how does it compare with a flat one. I'm going to explain you what I mean by hierarchical and flat later on. The third one is using this developed model, what insights can we draw from this images on Wikipedia? How can do we understand it a bit better? Yeah, so hope you're with me until now. I'm going to motivate my methods that I used. So we have a lot of data, so we wanted to use deep learning. We didn't want to use any classical machine learning for this, as we have a lot of data. The second thing is that the model we used for this deep learning has a lot of parameters, so we want to use a already pre-trained model. So we use this transfer learning paradigm. Third thing, so an image may have multiple labels, so we want to output independent probabilities for each label, so that one image can have several labels. So we use this binary cross entropy loss function that is standard. And then we have a pretty much structured data, hierarchical data, so we want to test using a model that is knowledgeable about the hierarchy. And then finally, we have this imbalanced distribution, so we want to apply some mitigation techniques to this imbalance. Now this can have a bit too much numbers, but just stay with me, and I'm just going to skip to the more interesting things. This is the model that we used, the baseline, the flat model. That means that the labels, they don't have any knowledge of each other. There's no parent-child links. They're only just flat Big Bang. We use an efficient net-based model that is pre-trained on ImageNet, and then we add some extra layers here, and then we output independent probabilities for each class. So this is the baseline. So yeah, just let's look at the first research question: how to mitigate consequences of imbalanced data. Before, we wanted to understand if it was better to structure our data in a flat or in a hierarchical way. So when the data is structured in a flat way, remember Francesco, the first guy, he had the flexibility of when he was constructing the data, he had the flexibility of encoding the data as flat. That means there are no links, none of this in the data, or hierarchical, where that means if something is classed with mathematics, it automatically got STEM. So let me give you an example. This image here is obviously history, and it's obviously maps and flags. So this is how it looks in the flat data. So the flat data doesn't even know that maps and flags is a child of places. But in the hierarchical data, we also get places and culture in the ground truth data. Do you kind of understand what I mean by flat and hierarchical? Okay. So we did a test to see which one of those data was better. And then, don't need to read everything here, but just see that the voted thing is the hierarchical data. So you see that it overperforms the flat data because the data is enriched with correct labels. That is, the semantics done but constructed by humans. And the second thing here is that the ratio of positive samples in the data increases, which is good in general. So from now on, we just use the hierarchical data. Okay. How do we mitigate imbalance in the end? To answer our first research question, there are 2 ways to do that. First one is by playing with the data, and the second one is by playing with the algorithms. So we tested both of them. A lot more numbers. So the data level techniques for mitigating balance. We tested. We ran the baseline, and then we ran augmentation, we ran undersampling, and then we ran oversampling with some heuristical augmentation. And then our conclusions, based on this bunch of numbers, is that naive augmentation is really bad. Undersampling, this one here, it keeps 80% of the data, but it retains 90% of the performance of this metric here that we consider the most important. And then it can be useful to save resources if you want. And then this one here is just bad as well, contrary to what is said in literature. So those are the conclusions from the data level. And then on the algorithm level, we use the baseline again. We have per class thresholds, focal loss, class weights, sample weights. And then these are the conclusions. Not very interesting for you to listen up, but the thing that concluded is good is this one, sample weights. That means giving different weights to the ones and to the zeros in the loss function. And yeah, here's some flags. And then some nice conclusions that we can draw here from our classifier is that it is not very good. Because as you can see here, our expectation is that the negative labels are to the left of the threshold and the positive ones to the right. And as you can see here, it's pretty much, most of them are pretty hard to recognize, whereas like a good threshold. So some conclusions we can draw from this is that, yeah, simple ways are pretty good. And then also moving the threshold so that you not always letting it be 0.5 is pretty good. And then the class separation is still pretty bad, so we need better labels and a better classifier. Yeah, so that is the conclusions to the first research question. We are at 17 minutes. Was it 20 minutes or 25, 30?
You have 25 or even 30 if it's
okay.
Keep going.
Okay. Okay, second research question. How does a hierarchical classification perform compared to a flat one? As I showed you right before, this was a flat model, and this is a hierarchical one. So the hierarchical model, we use pretty much exactly the same structure, but we add, we get this in the end, this block, as you can read from here. This block, it performs a matrix operation on those probabilities, and then it enforces that any parent labels have at least equal probability to the child labels. So this, let's say we have, I know that people is a child label of society, so it doesn't make sense in the hierarchical label that such a label predicts that people has a greater probability than society. So in that case, that block is going to make society have at least the equal probability to people. So that's what it does, and here's a link to that model. We didn't invent this. It was, it was state of the art on hierarchical multi-label classification. I was pretty impressed that on all of the papers with code showed that that model topped everything in all the data sets. So it was a pretty easy choice to use this model. Still, it sucks. We can see the numbers here. The flat model performs significantly better than the hierarchical one, proving wrong our initial hypothesis. Our hypothesis was that if a model knows that he knows of the hierarchy between the data, it should be better than a model that doesn't know anything. But this is wrong. And then we kind of make thinking why this is the case. We read in some feedback from the reviewers to the authors, and then I discovered better that this model that came out in 2021, it had never been used on image datasets. It was only used on datasets for functional genomics. So nothing to do with our dataset. So from this, we learned that you should not only trust papers with code, you should also read the reviewers' feedback, and also on what data they base this on. Then, what insights can we draw from the images in Wikipedia using our model? So we trained the model, the best looking model with the sample weights, and then we evaluated the model on the same data, which you might think is weird, but it's not. And here are the numbers we get. You may think that 52% precision is pretty bad, and 23 recall is pretty bad as well. It can be better, I agree, but it is not as bad as it looks, as I'm going to show you in a second. This is the predicted label distribution by our visual model. I'm not going to go into details, but we see that, yeah, STEM has 12%, places 40%. So this should represent the distribution of the topics, image topics in Wikipedia. Then this, I find this pretty interesting. I'm going to explain what this means. So in the x-axis here, we have the label frequencies in the data. That means here we have society, there's 25. That means that 25% of the images on Wikipedia are labeled with society, at least from our predictions. No, from the ground truth, sorry. And then on the y-axis here, we have the performance. We see that there is a pretty consistent growth. The more labels you have, the more data you have from that label, the more greater performance. So that's pretty obvious in machine learning in general. But then we have these guys here that have less than 5% appearance in the data, and that have pretty high performance. And those are maps and flags, sports, logos and symbols, and facts. And from that you can think that why the reason of that is, and then we think that either this depends on the pre-training that is done in ImageNet, and that is pretty reasonable for plants. There's a lot of plants in ImageNet, and the other thing is that the label is just easier to identify. Just maps and flags is always a map, is always a drawing. Yeah. Here's some nice looking flags, and then. That's what I just said. And then I just wanted to prove the usability of this model, why this is good. So as I told you, the ground truth labels, they are not human ground truth. They are ground truth by Francesco's work. And sometimes it misses like obvious labels. So yeah, sometimes predictive labels capture correct labels, missing at ground truth. So here are landscape. So according to the ground truth and to our predictions, you maybe cannot see here, but here there's landscapes. Here there's landscapes. As a human, I would pretty probably classify this as landscape, and this as well. But here the ground truth misses the landscape thing. So our model is capable of finding it. Same thing for animals. This is what the model thinks is animals, and in this case here for the fish, the ground truth doesn't think there's an animal there. So, pretty good. And then some more examples. Here, the ground truth doesn't see politics, but there's George Bush and his wife and some other people, so it's clearly politics. Here as well, the ground truth doesn't see. And here, Rafael Nadal, the ground truth doesn't see their sports, and then with this guy here, it doesn't see their sports either. Same thing for logos and symbols. So we see that there's a use for such a model, even though the ground truth doesn't see things. We complement with with correct labels. More examples, and I don't think I need to go into that. And some future work is we wanted to try with more classical methods. Despite what I told you that we want to use deep learning, because ORIS uses decision trees. As we have hierarchical data, is pretty obvious to use decision trees, so we want to do that. This one is the most interesting. So comparing the performance of the model with human labeled ground truth that we plan to do by using Amazon Mechanical Turk, and then also using the file name as a feature. And that's it for me. Thank you very much.
Okay, so this brings us to the opposition part. So, if you could forward and Matthias to one side. And also, has everyone filled in this checkbox too? Yeah, good.
Where should I be? I need to be close to my computer.
Yeah, so I don't know, maybe we can. Feels weird if you have the back to the audience. How do you?